We've been working with graphing rational functions. Now we're going to look a little more in depth, not when we don't have just a vertical asymptote, but what happens when we get what's called a removable discontinuity. This is going to be a hole in the graph rather than an asymptote. It's still going to be something that is not allowed in the domain because it'll be a denominator factor, but it's not going to be a vertical asymptote. It'll be a hole in the graph. So we wanted to go ahead and talk about how we set these up. So our objective is to be able to graph rational functions using removable discontinuities. So your steps are going to be, you're going to factor your rational function. You're going to reduce it if possible. Sometimes it won't reduce. And then you're going to use your graphing calculator. Let's take a look at what this could look like in our two different possibilities. So when it turns out to be a vertical asymptote, that's when the denominator factor does not cancel. So when that factor stays in the problem, then it's going to be a vertical asymptote. Here's an example. If you look at this problem here, where we've got the 1 over the x minus 7, when we look at this, the x minus 7 doesn't have anything to reduce within the numerator. So when we look at this, we're going to have a vertical asymptote out here at 7, where it's not going to go past that. Now, a quick look at the graph from our graphing calculator. If we look at this and we go ahead and graph it, notice that it's going to look like our hyperbola with 7 being the missing x value. And so when we draw it, we're going to go ahead and draw our close to the x-axis here, because that's an asymptote, and then close to 7, and then it comes up here and comes down to the x-axis as an asymptote and gives us that graph. Now notice that when the degree in the top is larger than the degree in the bottom, our horizontal asymptote is going to be y equals 0. But here we have a vertical asymptote at x equals 7. All right, now this one, notice that the degree in the top is larger than the degree in the bottom. What I want to do is mention that when we have a problem like this, we want to factor it. So I'm going to go ahead and factor the top here. And the top factors into x minus 5, x minus 3, all over that x minus 5. Now notice that the x minus 5s, that whole factor is going to reduce. When that happens, okay, so when the denominator factor does cancel, then we've got what's called a removable discontinuity. This is an open dot on the graph. This graph is going to look just like x minus 3. So if you have x minus 3 here, down at negative 3, you're going to draw a line like this. And what happens is it looks just like that. You might not even be able to tell that it's different than that. But when you look at the graph here, and then we examine the table, so let's go ahead and graph this one, get rid of this one, and graph the second one. So this is the second one. Notice it looks just like a line going through there, but when you look at the table, you notice that there's an error at 5. There's no x value allowed there because that would give us a 0 in that original denominator. So what we have to do is we have to take this and out at x equals 5, we're going to clear a spot right here at 5, and we're going to put an open dot in the graph there. It doesn't go through that point. You might not be able to see it on your graphing calculator. That's okay. It's infinitesimally small, but it skips over that point at where 5 is. So here, what we mark is we mark removable discontinuity, and we'll oftentimes abbreviate that as RD. just so that we don't have to keep writing out removable discontinuity. We have a removable discontinuity at x equals 5. So that, it's called removable discontinuity because that one point we remove and it's not continuous. It goes to that point, we have to hop over that point. It's not continuous through it, and then it picks up after that and goes on. So removable discontinuity because we can remove that one point and leave an open dot. All right, now let's go ahead and look at some examples here. So notice that this one, the numerator degree is smaller than the denominator degree, so we know that we're going to have an asymptote on the x-axis as part of it. So we're going to go ahead and factor it. So numerator's already just x minus 1. The denominator factors into, one hint is, look to see if x minus 1 is a factor, and it is. It goes with x plus 3 when I factor this. Now I look at this and these two do cancel, so I now get 1 over x plus 3 when I am graphing it. So this means one of the factors cancels. That's a removable discontinuity at that x equals 1, because that's the spot that cancels out. But notice the x plus 3 doesn't, so we're going to have an asymptote at x equals negative 3. So we'll go ahead and draw that in here just so we see it. Negative 3, our vertical asymptote. Let's take a look at what the graph looks like before we go ahead and fill in the rest of the information. Let's go to y equals. We're going to go ahead and get rid of the second one here. We're going to go ahead and graph the third one. So when I hit graph, notice that I get the hyperbola. Notice there at negative 3 is my vertical asymptote, and you can't even see at x equals 1 that there's a missing point. But if we look at the table, notice that there's an error at 1, and there's also going to be an error here at negative 3. Not allowed to have those 2 points. So I'm going to use this to draw my graph, and what I'm going to do is I'm going to draw, again, close to the x-axis and then go down and follow the vertical asymptote. Now I'm going to take this one down here and I'm going to go in over here. Now when I get to x equals 1, I'm going to stop. I'm going to put an open dot there and then just continuing getting close to, but not, this one looks like we're getting too close here. So we're going to get close to that x-axis after this for my hyperbola. So we have a vertical asymptote here, and we have an open dot. Those are the two values that would give us 0 in the denominator, and they're not allowed as part of my domain. So my domain is all reals except x equals 1 and x equals negative 3. Those two values are not allowed. Horizontal asymptote is going to be the x-axis, which is y equals 0. And then our end behavior, notice as x goes to negative infinity, the y is going to go to 0. It gets close to the x-axis, which is y equals 0. And as x goes to positive infinity, the y is going to go also to 0 from the other side. Get really close there as we go that direction. Let's do one more example. Let's see what happens with this one. So we're going to take, as we've been doing, we're going to factor the numerator since we can factor it. Notice the degree on the top is larger than the degree on the bottom. And so we're going to factor this into, I'm going to check to see if x plus 2 is a factor, and sure enough, x plus 2 and x minus 5 are factors of that trinomial in the top when I factor it. Then I have x plus 2 in the bottom. These cancel. That means that I've got a removable discontinuity at x equals negative 2. What would make that equal to 0 in the denominator? I don't have any vertical asymptotes because there's no other factors down here. So this would be a none, all right? I don't have a horizontal asymptote for this one either. So this would be none because the degree on the top is larger than the degree on the bottom. Let's go ahead and take a look at what our graphing calculator tells us for this graph. So if we go ahead and turn off the number 3 here, and then we're going to turn on graph number 4, which is this one. When we hit graph, notice that this one looks just like a line. It looks just like x minus 5. The key is it is just like x minus 5, that line, except at -2. So what I'm going to do is, just like this graph shows me here, this graph says it goes through -5 with a slope of 1. I'm going to draw my line here, so -5, slope of 1. And then when I get to x equals -2, I'm going to put an open dot there instead. So it looks like this. For my graph, we're at -2. I'm going to put that dot to show I'm not allowed to put in that x value. Otherwise, it looks exactly like that line. So my domain is all reals except x equal to -2. We're not allowed to put in x equals -2. Now our end behavior, notice that as x goes to -infinity, this is a line, it's going down to -infinity, so y goes to -infinity. And as x goes to +infinity, y is going upwards to +infinity as well. So what we've added to this, we still have our vertical and horizontal asymptotes, but we also have added the extra piece that if you factor and reduce a factor, that leads to an open dot in the graph. That open dot is called a removable discontinuity. So you draw your graph, when you get to that x value, you put an open dot and then continue the graph, but still draw your vertical asymptotes for the factors that do not cancel, and still evaluate it how you get your horizontal asymptotes. Use your graphing calculator to be able to confirm what the shape is and also to get some x and y values from the table.